This presentation is on the major dike swarms in Canada, including the timing, origins, and implications of each. There will be a primary focus on the Mackenzie dike swarm, which is located within the Canadian Shield. This presentation is going to discuss what a large igneous province is and how they are related to dike swarms. It will also provide an overview of what a dike swarm is and the pressure conditions that affect it. I will then go into great depth on the Mackenzie dike swarm's location and origin within Canada. The specific geology of the Mackenzie dike swarm will also be discussed. I will then go into detail about the Lac de Grasse dike swarm in the Northwest Territories and how it's important for kimberlite exploration. Dike swarms are associated with lips, which are large igneous provinces. The origins of some lips are still unclear. However, they may be associated with mantle plumes, rift-related decompression melting, extraterrestrial bodies impacting the Earth, or the replacement of a portion of the lithosphere with the hot asthenosphere. Lips are not associated with plate boundaries, yet they are associated with pulses of intraplate magmatism. They are not formed through plate tectonics like other geological features that can be observed like volcanoes, hotspots, or mountains. The image in the back of this slide is a map of the world showing some of the major lips around Earth. Although it only shows some of the lips, notice how they are not located surrounding plate boundaries like hotspots or volcanic arcs. They are quite dispersed. Dye-based dike swarms are related to these lips as they radiate out from the center, called its focal source. These swarms and provinces consist primarily of flood basalts and their corresponding plumbing systems. Mafic dikes are very fast-cooling intrusions of magma and placed in a formerly existing fracture system within the Earth's crust. The orientation of the dike swarms reflects the direction stress has been applied to the plate. Dike swarms are important because they allow us to identify a plume center. Every major breakup margin in Canada is thought to be associated with a lip, which gets identified by studying these dike swarms. Dike swarms are unique as they preserve the record of magmatic events. They are accurate time markers that reconstruct paleostress fields that have affected rock formations in the geological past. They achieve this since they exhibit the same trends as regional compressive stress fields and extensive tensional stress fields. There are more than 36 dike swarms alone in the Canadian Shield. Specific dike swarms contain various minerals and have a significant effect on people within Canada. The primary focus of this video presentation will be on the Mackenzie dike swarm. However, I will also touch on the importance of the Lac de Grasse in Northwest Territories and its importance to kimberlite exploration. The Mackenzie dike swarm is the largest dike swarm on Earth and extends across Canada from the Arctic, up here on the map, to the Great Lakes, which is near the bottom, in a northwesterly direction, as seen going up this way. It is in the Canadian Shield surrounding the focal source at the Coppermine River lava field, which is visible at the map right up here, which is what I'm circling. And then as you can see, as mentioned previously, that the dike swarms radiate outwards from that focal source. It is not deformed nor metamorphosed, so it's an excellent indicator of the stress field that was applied to the Canadian Shield 1.27 billion years ago. The dike swarm trends are parallel to the direction of horizontal compressive stress, and they are perpendicular to the horizontal minimum stress. From the focal source to 600 kilometers away, it has a radiating nature in the north-south direction, but then it gets a parallel nature from 6 to 2100 kilometers away from the focal source, swinging from northwest to southeast. As mentioned previously, the Mackenzie dike swarm originated 1.27 billion years ago as a radiating dike swarm, but becomes parallel at 600 kilometers from its focal source. This transition is due to regional tectonic stress from a ridge pushing from the Grenville Ocean onto the southeast margin of the Canadian Shield. It changes orientation because of the resistance between the focal area and Grenville Ocean ridge push. The mafic dikes cut through both Archean and Proterozoic rocks. These dikes are remnants of large volumes of basaltic lava that are in the form of flood basalts. It is postulated that there is a magma plume located beneath the focal source due to its radiating nature fast emplacement, and large amount of magnetism. A magnetic susceptibility study undergone at 400 kilometers and 500 kilometers away from the focal source indicates a vertical flow direction, whereas from 6 to 2100 kilometers it indicates a horizontal flow direction, following the pattern at which it radiates. This is a result of the vertical rise of magma within the melting zone of the plume core. As the magma progresses away from the focal source, it spreads laterally as opposed to vertically along the fractures from plume-induced uplift. This is able to explain why it transitions from vertical flow direction to a horizontal flow direction. The closest point to the focal source that can be analyzed to determine the geology of the source is from the Coppermine flood basalts. The stratigraphy at the Coppermine flood basalt has a northward dipping homocline resting unconformably upon a surface of early Proterozoic Watmate orogeny. Two of the lower units of the homocline contain siliclastic and dolomitic minerals, which have recorded uneven uplift and sinking prior to the Coppermine River basalt eruption. The lithology of the first unit is fluvial siliclastic rocks with a northern tilt. This then changes into shallow marine dolomites at the second unit. This subsidence, which is sinking, is then changed into uplift, which results in the unconformity of the upper strata of dolomite. The rock strata are generally able to describe the gradual sinking and its northern tilt as the lithologies change upward from siliclastic to dolomitic. Prior to the eruption of the Coppermine River lavas, the sinking is altered to uplift within the region, which results in an unconformity and karst formation in the upper portion of the strata containing the dolomite. Both the subsidence and uplift of the dolomites above the unconformity prior to the eruption is an indication of the thermal changes from an underlying mantle plume. This then furthers the hypothesis that the lip is associated with the mantle plume. The Mackenzie dike swarm is composed primarily of plagioclase, pyroxenes, and iron titanium oxides. This is because, as mentioned previously, it comes from flood basalts, and we know from lectures that basalts are primarily composed of pyroxenes, olivines, and you can find plagioclase and spinel as well as other minerals in it. The chilled margins are microferric with plagioclase dominant, augite, and then they also contain orthopyroxenes. Olivine is evident in some of the dikes, but sometimes it can be rare depending on where the sample is taken. It can be rare because sometimes you can find quartz in it, and as we know, quartz and olivine cannot form under the same conditions in the same area. Interstices are voids within the outer crust of the earth that have an opening containing air, natural gas, oil, or water. Interstices are filled with quartz, alkali feldspar, chlorite, amphibole, biotite, iron titanium oxide, and apatite. Magnetite and ilmenite are often present, with magnetite being the most dominant mineral. Alteration in the dikes is common and can replace up to 90% of the primary minerals. Plagioclase may alter into clay minerals, and pyroxenes alter into chlorite and actinolite within the Mackenzie dike swarm. Observing the Lac de Grasse dike swarm shows the importance of studying dike swarms and how they contribute to economic geology. Kimberlites can be found within kimberlite pipes, making dike swarms essential for exploration of diamonds. The Lac de Grasse is in the Northwest Territories, as seen on the map above here. It is located within the Archean Slave Province, which is dominated by metasedimentary rocks and granitoid rocks. There are 5 unique dike swarms in this area, which are aged between 1.27 to 2.23 billion years old. Many of the characteristics from the Mackenzie dike swarm that we studied can be applied to this dike swarm, so I'm not going to go over the logistics of pressure affecting the orientation of these dikes. I will, however, discuss how important dikes are and how important it is for kimberlite exploration within Canada. There have been over 150 kimberlite pipes reported in this area. These kimberlite pipes are oriented in the same direction as the pre-existing dike swarms, which can be seen at this bottom image right here. These dike swarms and kimberlite pipes are also oriented with the fault and fracture zones, so it's all interrelated. This orientation is a key part of kimberlite magmatism. The emplacement of dikes is very important for kimberlite exploration. Dikes are structural features that allow kimberlite magma to ascend so that the resources can be obtained by us. This example of the Lac de Grasse dike swarm is one example on how important it is to study dike swarms, specifically within Canada. The 2 dike swarms discussed in this presentation were over 1 billion years old. As mentioned as well, the most common origin of dike swarms are from mantle plumes, but they can also be associated with rift-related decompression melting, extraterrestrial bodies impacting the Earth, or the replacement of a portion of the lithosphere with the hot asthenosphere. Dike swarms are a key part to understanding the Earth's past since they record the direction of pressure on the Earth's crust. They also play a key role in Canada since they allow kimberlite pipes to ascend and be explored for diamonds.